Hi everyone, this is Lab 4 on Oscillations. So the purpose is to describe harmonic motion and analyze motion of springs and gravity in effect. So fundamental physics principles and models. On the right, we're going to see that is an image on the top image of the model that we used. And the bottom is the tracker data in the video that we used of the spring and mass. On the left, there's the force equation for the springs. There's the equation for the time period of one spring in harmonic motion, and then there's the energy, the potential energy of a spring, potential energy of gravity, and the kinetic energy of a mass. So main result preview there. On the left, that graph is showing the change in energy versus time, and so change in energy overall is always zero, but delta U of spring changes, delta U of gravity changes, you go up and down. The delta U of the spring changes as it compresses or lengthens, and then delta K changes. And on the right, we see the change in Y position. The blue is the model, red is the experiment. They're pretty similar, and below that is the X and Y, or X and T position between model and experiment. Oops. All right, assumptions. So we're assuming that the spring is a perfect Hooke spring that'll follow Hooke's law perfectly. We're assuming that G equals 9.8 meters per second squared, and that air resistance and friction are negligible in our coding. So the system is the mass object that's attached to the spring at the end. The surroundings are the earth and the spring. The earth, applies gravity, and the spring applies spring force. So initial conditions for the model. This is the initial position vector and velocity vector. The velocity vector was found with an arithmetic average of the first two values taken from the tracker. And G equals 9.8 is our assumption. The spring constant was taken from the video at 6.83, and 1.261 was relaxed, which was just a little more precise of the initial vector. So the coding, this is the bulk of the coding that we used, and so we use position update formula, and we use V final because the spring force is not constant throughout the entire time. So that force is not constant. We cannot use the average to update the position update formula. We have to use V final. And you can see how we update the velocity, update the position, and update the spring force, L hat, and what S is. And then we calculate all the changes in energies to be able to graph these. Similarities and differences. Friction and air resistance affect the real-world model, whereas this does not come into effect at all. We don't program it into our model. And the spring may be aged, and maybe not a perfect Hooke spring. It might have rusted, it might have changed or deformed in some shape or form over the time of its existence. I hate to say that, but source of air, friction, air resistance, and digital measurements may not be precise enough from the video, so my measurements on the on tracker might not be precise enough to accurately go out throughout this experiment. What does it mean? Energy is always conserved. Delta E is always zero, as we can tell from this graph, and you can visually see it too, as the sum of all of these, as of the green, the red, and the blue, always equals zero. What does it mean, part two? So we're looking at the period estimation in the x direction. It looks about 1.6. However, it is about 1.7 in the y. I'm not sure why this is, which is strange for x position and y position. Ideally, they're both the same. This is an interesting phenomenon that comes out of both the experimental and the model. But again, they're roughly the same, which is what we would expect. Thank you for watching.